Okay, I want us to look through a couple of these slides, so please be using your notes to fill in any potential information that is necessary. So we've already been looking at spectra. You've been doing that via your spectroscopes. And we have talked about the neon signs. We looked at the gas tubes, and you guys, we all made some inferences about that what we were observing was unique for each of those different types of gases in those tubes. So let's just look back over each of our different types. So we have continuous, which you see as the top one. We have absorption, and then we also have emission. And I think we can all agree here that absorption and emission have some type of relationship to one another. Okay, we've also had some discussions about the visible spectrum here. When we look at white light, we place that through a prism that breaks up into all the respective colors along the visible spectrum of the electromagnetic radiation chart. Okay. Now, continuous spectra is what we see with white light or incandescent light. And so we use a prism or a diffraction grating to separate those colors, and then we see those dispersed among that as a continuous spectrum. And there's smooth lines as that transitions through. So white light makes up all of those components of the visible spectrum. Now, what's really going on with absorption spectrum is that we have dark lines superimposed over our continuous spectrum. But what's causing that? And so what situations are we dealing with? We're dealing with cool gases higher in the atmosphere, and as that white light passes through that, what happens is that we see which wavelengths of light that particular gas in the atmosphere is attracted to. And so it absorbs those, and the rest continue to carry on through the atmosphere. And so we get a chance to see which wavelengths of light that particular gas is attracted to. Now, line emission, what's going on here? Generally, we have a gas that we've contained at low pressure. We're adding an electric current, and then we're seeing that excitation of those atoms. Okay, they absorb those specific wavelengths of energy, and then they move to an excited state from that ground state. They fall back to that ground state. Okay. And one thing I want us to discuss too is make sure we understand that as far as our line emission spectra is concerned, it's much like things are with us as humans. Our DNA is something that is specific and unique to each of us. Your fingerprints are something that is specific and neat to you, and so too are line emissions. We can study those line emissions to give us information about the identity of the different types of gases that are making up that unknown substance. And that's just what scientists did over time. So let's look real quick at a line emission set of charts. So as we move through this chart, we can see here from hydrogen to helium, carbon, nitrogen, oxygen, you can see here that each of them have their own unique set of wavelengths that they absorb and emit. And some are much more complex than others. We'll just look at a few more just to go ahead and confirm that we know that line emissions are unique and that the way that electrons behave with light is unique to the identity of the atom. Okay, this last little bit is talking about that quantum of energy that we've already discussed, as well as talking about that ground versus excited state. So elements absorb specific frequencies of energy in the form of those wavelengths, and they become excited and move from their ground state to some higher energy level from gaining that energy. And then what happens is they can't hold on to that energy indefinitely, so they have to release it. And as they release it, they return back to their ground state from the excited. That energy is ejected from the atom, and we see that as some form of colored light or along your spectrum here, your emission spectrum or absorption, we see the presence or absence of those lines of wavelengths that it absorbed and emitted. Have a wonderful day.